Thank you. Hello, everyone. Yeah, my name is Benedek Gagyi. This is my Twitter handle. I posted these slides on Twitter, so if you prefer to follow along on your own device, you can do that. So thank you for the introduction. Those were a few personal things about me. And one more thing about me is that I really, really love tea. Yeah, I really do. And the interesting thing about tea is when you start drinking a certain type, the first thing you notice, your first point of contact, is the taste. How does it taste? But as you get more into it, you drink a bit more, you start to wonder, OK, where did this tree come from? When was it picked? How was it processed? And as you get even more into it, you start to wonder, OK, how do I feel after drinking this certain type of tea? How will I feel in the long run if I keep drinking this tea? And why I'm telling you this is because I think new technologies are pretty similar to that. You see, when you first hear about a new technology, a framework, a library, the first thing, your first point of contact is the API. How does it work? How can I make it work? But then as you get more familiar with it, you start to wonder, OK, what happens if I add this to my product? What effects will it have on my code base? What effects will it have on my team? So like the title says, today I'm going to tell you about a cross-platform architecture that's based on WebAssembly. And I'm going to tell you all this in the prism of our experiences in the Join Me team. So first of all, I'm going to tell you what WebAssembly is, obviously. Then I'm going to tell you what our problems were at Join Me, how this kind of architecture solved them, and what we learned through this journey, what were the biggest problems we faced, what were our biggest fails, and how we tried to mitigate them. So obviously, you can't really talk about WebAssembly without answering the question, what is WebAssembly? The simplest way to define it is by saying that it's a binary format. Basically, you take a piece of code that's written in C, C++, or Rust. You put it through a compiler, and the resulting file will be in WebAssembly format. And this WebAssembly format will be understood by all the browsers. So basically, you take a piece of code that's written in C, C++, or Rust, and you run it on the web. That's pretty cool. Another way to define it is by saying it's the next step in the web performance, in JavaScript performance. And that's obviously true. It's a binary format, so it's inherently compressed. There's no interpretation step. There's no need for warm-up time, so the performance is more consistent. You have a chance to do manual memory management. There are really cool CPU features, and so on and so forth. So that's true. It's really making JavaScript and the whole web faster. Basically, a really simple analogy would be to say that JavaScript is this really comfortable family car that is really easy to use. The whole family fits in there. It's not too fast, but you can do anything you want with it. It's fine. And WebAssembly, on the other hand, is like a spaceship. A lot more complicated, but on the other hand, you can do almost anything that you can imagine with it. Another way to define things is by saying what they are not. So WebAssembly is not a solo mission. It's backed by all the major browser vendors. Google, Microsoft, Apple, Mozilla, they are all behind it. They all want it to succeed. So that's pretty cool. And also, it's not the next Java applet. It's not running in a sandbox. It can do whatever JavaScript can. It can access the DOM, it can network, it can do everything. So we're not doing that fail again. And also, sadly, it's not ready yet. What you can use today is an MVP version that's feature complete, but a lot of cool new things are going to come. So if you're interested, just keep your eyes open, because the next few months will be pretty amazing. OK. The last definition I'd like to present you is the one I like the most, and it was given by Lynn Clark. She said that WebAssembly is a way to run programming languages other than JavaScript on the web. So imagine, there was a piece of code written maybe 10 years ago. Nobody wanted to run it on the web. But simply by running through a compiler, you can put it on the web. So people put like Quake 2 in the browser. I think that's pretty amazing, and it opens a lot of really interesting possibilities. OK, so let's see the Join Me story. What did we do? What happened to us? So Join Me is a screen-sharing online collaboration tool that was first released in 2011. First for Windows, then the Mac and the Android and the iOS versions quickly follow along. And in 2014, the team realized that, OK, we need the web as a new platform. But that was quite a challenge. If you had the same problem today, you'd basically have two major options. Either go native, write a native app for each and every single platform. Basically, you will have as many apps as many platforms you have. Or go with the web-based cross-platform solution, something like React Native, Electron, NativeScript, Ionic, these kind of things, where you write everything in web languages, so HTML, CSS, and JavaScript, and then compile it to each and every single platform. Basically, you have only one source code base that will be spread around to all the platforms. Both of them are really cool and really useful in many situations, but you have to see they have their drawbacks. So if you're using React Native or Electron, you're most probably going to have a performance hit. Also, the look and feel, the native look and feel, sometimes can be really hard to reproduce with CSS. So UIs on Mac look different, UIs on Windows look different, and you have to reproduce that feeling, and that can be hard. And also, if you want to scale really fast, it can be an HR nightmare. In my experience, if you want to hire one good JavaScript developer, that's pretty hard. If you want to hire 5 in the same time, that's practically impossible. On the other hand, if you're going with the native approach, there are also problems. The biggest one being that you're solving the same problem a few times in different places. What this means is you have different solutions, because you're not going to write the same code with different technologies on different stacks. And this could result in situations when you have a bug that's present in all of your platforms, but you have to solve it in different ways on each and every other platform. Basically, as many platforms you have, as many times more work you have to do. And also, versioning and backwards compatibility is just a mess compared to the web, where you just refresh something and everybody sees it the next time they load the page. So what we wanted, and what everybody usually wants, is not one of the extremes, but a sweet spot somewhere in the middle, where you can have both of those words that are good, but you kind of avoid the bad things. There are many ways to do this. The one we chose was in 2014 was based on a tool called Emscripten. Emscripten is a compiler that takes a piece of C++ code and compiles it into JavaScript. Yeah, I know, C++ into JavaScript. The resulting code is a mess. It's not human readable. You don't want to check it out. It's basically black magic, but it works. It can handle almost anything that you can do in C++. The performance is really, really bad, but it works. So what we could do with Emscripten was take all these different platforms, take out the part that's shared between them, basically the business logic, rewrite it in C++, and then compile it to each and every one in their own way. So C++ is a really portable language. It's pretty trivial to compile it to Windows or Mac and so on. And thanks to Emscripten, we could compile it into JavaScript too and run it on the web. So we took out this part, and because we are really creative people, we call this part the common. So I'm going to refer to this as common. So this is just a part of our code written in C++ that's shared between all these apps. You see how it's the middle ground? We have a native part, but also a part of the code base that's shared between all of our apps, independent of the platform. OK, but what does Emscripten has to do with WebAssembly? Well, it's basically WebAssembly if you're a JavaScript developer and you pay attention that there are only 2 equal signs. So Emscripten right now is the de facto compiler for WebAssembly. And it's so simple, because if you have a setup like ours, where you compile C++ into JavaScript, by changing one single flag, you can make it compile into WebAssembly. So it's not like you have to rewrite everything and redo all your CI. No. Just a really small detail. So basically, this allowed us to have 4 years of experience in a technology that's only 1 year old. Basically, we are the dream of recruiters. Because we've been doing this for 4 years, and the WebAssembly is only 1 year old. OK, so we did this. We changed that flag. And without any other changes, the next thing we saw was that our payload has decreased by 15%. So yeah, all the things I said earlier about performance, yeah, they are true, and they will get even better as we go on. Okay, enough of the commercial time. Let's see what was hard, what we had trouble with. I'm going to separate this into two different parts. First, I'm going to focus on the technology, and second, on the human aspect, on the team aspect. So, the first thing, we wrote our common code in C++. And C++ is a great language, obviously. It's really portable, and it has a huge community, so you have libraries basically for everything. But of course, it's not perfect. It's usually really slow to compile. It has a really complex CI because of the many different compilers. And it has a really steep learning curve, especially for JavaScript developers. But as we went on, as we kept adding features, we realized, we kept asking ourselves the question, does the language really matter? Because what you're going to put in this shared code base, in this common, is the business logic. And the business logic should be language independent. It's just a few ifs and a bit of state management. It shouldn't have anything really language specific, like pointers or stuff like that. It's just the general logic of your application. And another reason why we tend to keep with this approach that we put only business logic in there is because every time we put something platform specific in there, it came back to haunt us. Every time. It was always a really bad decision that we realized later on, obviously. Just to tell you an example, it seems like a really good idea to add an abstraction layer over handling video and audio. That's really nice, and everybody who uses the common just have to, OK, open the video connection, close the video connection. Seems fine. But the thing is, on the web, on the browser, and on native clients, the underlying layer is totally different. It's really, really hard to handle. So we had to keep up this huge amount of code that added this abstraction layer when each platform had this already in a much nicer way. So we try to get rid of that, and just everybody handles their own video connection on their own. We just give them a feed and take it away. And that's one of the examples, but there were a few. And every time it hurt a lot to get rid of it. So another question we were constantly asking ourselves was, OK, you have these front-end platforms and the shared code. How thick should this be? Should you share as much as possible? Or should you keep it as thin as possible and only add things when they are presented all 5 of the platforms, or all the platforms that you have? Well, in our experience, it's a better idea to make this abstraction somewhat thin. And if you really have things that are shared, for example, between these 3 platforms, but not the other 2, then just add one more extra abstraction layer above. And then they can share the code that's actually common between them, and you're not forcing anything on the other ones. So you have all these layers. Cool. You have to connect them. How do you connect? How do you do that? Well, obviously, you just plug it in and it works, right? Because we computer scientists are really, really good at connecting things in a simple way that works every time. Yeah, obviously. I see some of you are smiling, maybe because you are Apple users. Yeah, you have it worse. It's just a mess. So obviously, then we somehow managed to do it. We come up with a solution, but these solutions are not that stable and not that safe. It works, but I'm not sure you want to get really close to that. So we had this constant fight where we had these layers. They were really nice on the inside, but when we had to connect them, they were causing errors. The APIs didn't really match, and so on. So one thing that we kept coming back to was, you should really respect your contract, your API. Because if you keep changing it, all the platforms that depend on it are using the same API, but in slightly different ways. So even if you're making a change that you're pretty confident won't cause any troubles, you can be sure that on at least one of the platforms, it will cause something you haven't known about. It's simply, there's no human who can keep in their head all the ways that one API is used. So it's a lot better to try to keep it as fixed as possible. But you can't keep it fixed forever. You have to change it sometime. And when you change it, how do you make sure that it's stable? You're not breaking all the platforms. Well, you write tests, obviously, because writing tests is really simple, and it's always sure that if a test says everything's OK, then it is OK. You can release it. Your users will like it. The thing is that even though you can have a really good coverage, that doesn't mean that you can be sure that your code is not broken. So you're writing tests. You're writing a lot of unit tests, and that's fine. You have to do that. They are really fast, really cheap, cool. But they don't guarantee you that these layers are connected as they should be. How do you check that? By writing integration tests. The problem is, if you have many platforms, you have to write as many integration tests as how many platforms you have, because the integration is kind of different. There's a different tech stack. You have to check it in C++, in Objective-C, in JavaScript. It's always a bit different, so the cost of writing these tests is a lot more than you'd expect. And another approach that people tend to use is they say that I don't need integration tests. I just write an end-to-end test, and if it works, it means that the layers are connected properly, right? Well, I could debate that, but the worst thing is that end-to-end tests are even more expensive. Again, you have to do them for each and every single platform. And what's more interesting is that if you have so many platforms, that usually means that you have all these different people using different platforms communicating between each other. So in our case, that means that you can have a meeting that's hosted by a Windows machine, but somebody joins from an Android phone and somebody else joins from the browser. There aren't that many tools who can handle this situation in one test. So imagine a tool where your first thing you write is, do this on Windows, then click on this on the Android app, then click on this in the browser. There aren't that many tools who can do this. So we had to write a bunch of test frameworks for ourselves, a lot of test APIs, and it is still a lot of work. That's obviously you have to do, but expect it to be hard. It's not as simple when you have only one platform. So if you wrote some tests that you're confident in, you have to add them to your CI, because having a good continuous integration is really important, especially in these situations when you have so many different platforms, different ways to build. So please, build a good CI as early and as fast as possible. And the last thing I like to mention is debugging. When we were back using Emscripten, the resulting JavaScript code was huge. Imagine 150 megabytes when it wasn't minimized. And that means that when you try to debug it in the browser would just crash 9 out of 10 times. So that was pretty hard to find out, OK, what's wrong in the web? WebAssembly made that a bit easier because you can have C++ source maps, so you can basically debug C++ code in the browser. But it still has its problems, so we tend to go back to our good old magic trick that's called printf, and just introduce console logs in the code and see what happens. OK, let's see how it affected our team. Well, the biggest thing that we kept coming back to was how do we organize our teams? Because there are many things to do, and it's not trivial. It's not like just one team can do everything, obviously. So I'm going to tell you about two extremes. All the things that we tried were kind of a mix of these two things, but I think it's easier to grasp the differences between them if we talk about the extreme ends. So one extreme would be to have feature teams, where each team is responsible for one feature, meaning one platform, and the platforms could be Windows, Android, iOS, and so on. But one of the platforms would be the common code itself. So there's a team whose job is to maintain and upgrade this shared code base. Another approach, or the other end of the spectrum, would be having cross-functional teams where each team is able to ship a feature and can do everything they need from backend, the common code base, and the front end too. So the first big difference between these two is the approach that we saw that people kind of adopted. When you had feature teams, so like the more horizontal teams, they had this product mindset. They had their own product, and they wanted to make as good as possible. That's really nice, and especially when you have this common code base, the people working on it were really focused on have it performant, nice, keep the code clean, and so on and so forth. On the other hand, when we had cross-functional teams, it was more like an open source approach where everybody just did small modifications in all the code bases where they needed to, but nobody was really paying attention to the big picture, keeping the code clean. Another interesting aspect of these is how the work goes. So when you have feature teams, they only work on one code base, so they are obviously really fast. They can ship a product in no time. But the problem is there's queuing, because all of the front-end teams depend on the team that's developing the common. So even if that team working on common is really fast, they will still have a long queue of work to do, and sometimes teams may have to wait on them. On the other hand, if you have a cross-functional approach, even though you have to know a lot of code bases, which takes a long time, you are able to ship it alone, meaning that you don't depend on other teams. So it's more democratic. Another difference is from the product owner's point of view. What a product owner sees in these situations is that feature teams have a really good ownership. If something's not working on the Windows app, for example, they know where to go. Who are the people who are able to fix it? On the other hand, in this case, because of the queuing, it's really hard to give a good estimate. Okay, when can we ship this feature? For cross-functional teams, these estimations are really precise because they do all the work. They don't depend on anyone else. So just to sum it up, I think the feature team's approach is better when you have to take really big steps. And the cross-functional team approach is better when you're making small adjustments, when you're fine-tuning your application. Obviously, again, I have to repeat this. You won't ever go with these extremes. You'll have teams that are mixed, somewhere in between, but these are the main things that are going to happen. For us, the biggest takeaways from the team management, the human side, was that, first of all, trust is key. Because you have all these dependencies and all these many teams working on a shared code base, you really have to trust each other. There's no place in saying that, don't let them do it, we can do it better. No. If you have that mindset, you have already failed. Another thing that's kind of obvious is scaling is really hard. It doesn't matter how you organize. If you want to add 10 more people, it's going to be really hard, a lot of things to learn, a lot of toes get stepped on, and so on. So scaling in general is really hard, but in this particular case, we found that's even harder than usual. Another thing that we kept doing, and it was wrong, was communicating to PRs. So you have all these code bases that are touched by many people, and you have to work on it, and you say, like, yeah, I know how I'll solve it. You code your solution, and you just send a PR. But there are other teams who are working there, and they say, no, we discussed that we're not going this way, we're going to do another way. And these big debates come up, and these PRs are never merged, and we keep coming back to them. So no, don't do that. Communicate earlier. When you start developing a new feature, something new, discuss it with the other teams. Keep the ideas flowing, because it's a must. You can't do it any other way. And the last thing I'd like to put a big accent on is how good it is to have a diverse team. In general, diversity is always good. But in this case, imagine that if you have like a React Native or Electron app, all your developers have JavaScript backgrounds. So for a problem, they most probably will have the same approach to solve it. But in this case, in our case, we had C#, C++, Objective-C, Java developers, and obviously JavaScript developers. So when we had a problem in the shared code base, we had a lot of different viewpoints. So I'm pretty confident that because of this, we managed to find better solutions. OK, so this is all cool and well. Architectures are nice, but there's a misconception about WebAssembly that it's really, really complicated to get into. So in the last few minutes of my talk, I'd like to show you actually how easy it is to get started with it. I could show you how you can compile a bit of C++ code into WebAssembly, but something even more interesting and even more fun is using AssemblyScript. AssemblyScript is a compiler made by Daniel Wirtz. You can find him on Twitter by decode.io. And what it does is you write a piece of code in JavaScript, more precisely in TypeScript. But instead of using the typical TypeScript annotations, you have to use special ones. And because you use these special ones, this compiler is able to compile your TypeScript code into WebAssembly. So basically, you have a piece of code, you add just a few annotations, you compile it to WebAssembly, and if you are doing it right, you get better performance. Performance in general is really complicated. Performance in WebAssembly is even more complicated, so it's not automatic, this performance gain, but there are many situations when you can actually do that. And I'm going to show you how this looks. So, can you read the code? Should I make it bigger? In the back, please wave if you can't. OK. So what I have here is a simple function that calculates the Fibonacci number. And as you can see, I added a few extra annotations, I32. What is I32? It's 32-bit integer. Basically, it's a type like you would have in C. And the other thing I have is a really simple page where I load the WebAssembly file. You see all these lines. Please don't remember it. Forget it. You never saw it. Because this is an ugly way to load it, and it's going to get a lot nicer in just a bit of time. So don't remember this. What we have here also is a simple function. It's basically the same function we have in the other file, just in regular old JavaScript, so we can compare the two things. OK. So how do you make this compilation? It's really simple. You just say ASC, the source file, and the output. Enter, and in a few seconds, done. So if we go back to our editor, we can see that a fib.webassembly file has appeared here. Cool. So let's test it. We have a really simple page, so the page itself is not showing anything. But in the console, we can see that we have this WebAssembly object with our function on it. So basically, we can call webassembly.fib 4, 5, 6. You get the hang of it. It's working. Yeah. But what happens if I give it a really big number, like 300, minus something? I'm pretty sure that the Fibonacci number should be positive. What's happening here? Well, if we go back, you can see that we used I32. But JavaScript only has floats, which are 64-bit doubles. So what happened here, it was a really simple overflow. Our numbers weren't big enough to hold the numbers that we wanted to put in them. It's really easy to fix this. You just switch all of the I32 ones to F64. Yeah, changed it. Recompile it in just a few seconds. Reload the page. And now it's better. Just to make sure, let's test it with the plain old JavaScript one. Yeah, it's the same result. So basically, I showed you that I'm actually running WebAssembly because without WebAssembly, you're not able to use 32-bit integers in JavaScript. You only have floats. So yeah, that's a really fast way to get started with it. It's really cool to play around with AssemblyScript. If you have the time, I really encourage you to do that. So like I said, it's going to get even more easier to add WebAssembly to your web page. For example, there's already a Webpack package that where you just simply import a C file, like you would import a JavaScript file, and it will do everything in the background, and you can just use it. Magic. The tooling is going to get a lot better, so you can rely on it. As a closing words, I like to quote Brandon Eich, the inventor of JavaScript. He used to close all his talks by saying that, always bet on JavaScript. And I think from now on, we can add always bet on JavaScript and WebAssembly. You see, like MPJ said earlier, it's going to be interesting to see what sticks from the JavaScript ecosystem and what will move to WebAssembly. But I think even though that many good things come to an end sometimes, and really nice careers have to end, JavaScript and WebAssembly as a team will be here for a really long time. And we're going to have fun writing it together and talking about it together at conferences like this. Thank you very much for your attention.